Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Hi and welcome back to the Neil Ashton podcast. So today's episode is with somebody who I've actually really enjoyed getting to know better and chatting at various conferences that we've attended together and some mini symposia that we've done, which is Johannes Brandstetter. So he's got an interesting profile because not only is he a professor in Linz at the Johannes Kepler University in Austria, but he also founded or co-founded a startup recently called MEAI. His background is one that is very well positioned to help advance the state of machine learning for CFD and I guess CA more broadly. And yes, this is an episode on machine learning again. I sometimes feel bad that I keep doing this, but I think this season there's a mixture of episodes, and I still feel that there is value in going through the machine learning topic, and it's selfishly something that I'm constantly interested in learning more about, and learning more about it is one thing that I always do when I speak to Johannes. And he has an interesting background because whilst he has a high energy physics background that he did, and he was at CERN and he worked in that sort of area. He then moved into the machine learning side, having spent time with Max Welling at the Amsterdam University in the machine learning lab. And then I think he also, I don't think I know that he was then at Microsoft Research where Max was also at. And so the two of them collaborated a lot. If you don't know who Max Welling is, first Google his name. He's one of the pioneers of machine learning, but I also did an episode with him in the last season that I think was really interesting. I think he must have been inspired by Max a little bit, even though we didn't talk about it in this episode, because Max also has been a serial startup founder. And the reason I said that he has an interesting background is because whilst he was at Microsoft, he also worked on the Aurora machine learning for weather and climate project that I think is extremely useful when you have people who have gone through these major projects in another field, because they bring with them lessons and learnings that are important. And what Johannes has been doing is, first of all, bringing a very academic mindset to this. Academic in the terms of publishing and transparency, which I think is very welcome. So you'll find in the link in the YouTube a couple of the papers that he's published and his startup has published, a new sort of transformer-based model that at least from my reading, is unique and certainly seems to be at the one of the most cutting-edge and state-of-the-art models out there today, both in terms of conceptual, but also the accuracy on the data sets that they've shown. But I admire his vision and his willingness to try and solve the problem rather than being focused on the model. As in, some people seem to, once they come up with a model, fixate on that being it, rather than being willing to consider that their model may be the right thing at the time, but then there'll be other models that get better. And his willingness to accept that, I think, is a breath of fresh air, and definitely will help the community to evolve. So that's what we talked about today, really. We tried to go through and discuss, more of the general topics around machine learning, but really diving into this transformer-based approach that he has, and trying to understand some of his thoughts around the similarities to null operators, some of the slight differences, some of the links to, graph neural nets and mesh graph nets that probably most people are aware of. And then we talked a little bit about the process of forming the startup and some discussions around future topics. as with anything, I always feel bad because I finished the episode and I think I really should have discussed more or dived into certain topics. But I'm conscious it was already over, an hour 20, and people will, fall asleep listening to some of these episodes. But hopefully it's enough to spark your interest and encourage you to read more about the topics that we discussed. And please leave any comments or let me know if you have any suggestions for other topics. But for now, please sit back and enjoy what I found an extremely interesting episode with Johannes Brandstetter. Cool. All right. Thanks for joining me today. I wanted to have a chat with you for a while. We've had some nice discussions over wine and coffee, but nothing public. So this is the public version of our discussions. But maybe it'd be good for people to learn a little bit more about you, where you're at today. Who is Johannes?
Thanks. First of all, thanks really, Neil, for having me. It's a great pleasure finally seeing these guitars here in a one-to-one setting, so to say. My background is actually I'm a learned physicist. Some say a failed physicist. But after my PhD, I switched to machine learning, as many people also did. I spent time with Sepp Hochreiter and 3 years in Amsterdam with Max Welling. I was in industry for 2 years at Microsoft Research. And there at Microsoft Research, I really discovered my likings for large-scale simulation, especially for weather and climate modeling, because these are like some of the biggest problems you can have and you can tackle with machine learning. I also saw the transformative impact on these systems, and that was then the point where I decided to do my own thing, but to apply it not to known problems like weather, but rather uncharted territories like engineering, simulation, and this kind of thing. And I decided to get my own group at university to build up my knowledge base back in Austria, where I'm coming from. And along the road, it also happened that I founded a startup, MEII, where we do these simulations at scale and where things are coming together with a bit more compute and a bit more resources.
Nice. Well, we need to dive into each of those. But maybe the first one was the Aurora project. I guess this is maybe... It was simultaneously both a motivation, I think, certainly for me and others who saw what was happening in weather and climate and was saying, surely we could do that in engineering. But also it was an example of a real large scale project. So what was it like working on that Aurora project? What was the key lessons you learned both from maybe an ML point of view, but also a project and a team point of view?
So the actual Aurora team was pretty small. I mean, all the credits to Chris Bodnar, Wessel Brownsma, Megan Stanley, Anna Lucic, who did all the heavy lifting afterwards to finalize this project, to train, to build the data loader. The Aurora the learnings, I think, are threefold. First of all, with computer vision tricks, you can get very, very far in engineering or scientific application. In the end, it was a swing transformer trained in a 3D swing transformer. Secondly, that the data engineering is potentially the hardest one. And thirdly, that weather has a very unfair advantage for machine learning because nobody knows how weather is functioning. So you will always train a machine learning model on like actual data, which basically has the actual physical laws hidden, whereas the null numerical methods, they have to come up with these laws by themselves. And that already brings these key interests of mine, which is that neural surrogates will never replace numerics. They will just be a different branch, which, depending on how you play the card, acts in your favor. And that it's all about engineering and scaling these things to these basically to these problems where they really have an impact and where it really matters. And the impact for Aurora, you could see if you look through through these downstream tasks, that the larger these challenges are, the more impact you can basically generate.
Yeah, it seemed to definitely spur on, and now it seems that there's been so many of the weather and climate models, it's almost got not congested, but there's quite a few coming out, and so it's not obviously so clear how each are progressing past each other, and how much are those of just an individual groups need to have their own model, if you know what I mean. But I guess one of the big things that I wanted to discuss today with you in particular was to dive into, I guess, where machine learning, how can I phrase this? Machine learning for engineering, for CFD, for CAE, it's something I've spoken to a few people about, and there's a lot going on, but it hasn't always been so clear where the big breakthroughs will be, or how good are we today and where we're going. It still seems a congested space with different opinions, with pins on one side and then these sort of mesh graph nets and other things. So it's a bit of an open-ended question to you, but I guess, like, where do you see the state of the art? What's been your journey from the sort of mesh graph nets towards your current thinking? Like, how have you tried to solve this problem, I guess? And let's take CFD maybe is the problem, like automotive aerodynamics, for example.
Yeah, that's a very good, it's my favorite topic, actually. Making the connections to weather, let's say what basically was driving this weather modeling. I would say that NVIDIA was the first with the ForecastNet paper to bring out a model which worked or was trained on Era 5, which is a publicly available large-scale data set. Depending on how you sample, you get roughly a petabyte of data or a few hundred terabytes of data from it. And then you do basically mean squared error training. That was the scene set. And as soon as this problem was defined, of this input-output relation, of this metrics, of what to test, then people did what they do best. They optimize on these sort of problems. If we go to engineering, things are very different in many aspects. So first of all, we don't have this data set. We don't have an Era 5 data set. And even if we had an Era 5 data set, there are now at least 2-3 publicly available CFD data sets. Needless to say that my favorite one is the TribeML data set, which are industrial standard. But even if these data sets are out there, people don't know how to train on them, and everyone trains differently. And this comes from the fact that we just don't know what we really want to optimize. There is people who subsample parts of the surface and map to pressure values on the surface, people who subsample part of surface and volume, and so on and so forth. So similarly to weather, we have to figure out what's the right task, what's the right learning task, which we have to do, or the tasks, in order to really develop the right models and the right frameworks for that. Secondly, I think what is also very different to weather is that we have this input-output relation. So in weather, it's always clear you take time t and you map to t+1. That's basically a segmentation task on steroids, because in the end, every pixel on the Earth gets mapped to a pixel on the Earth like a time point later. Which you can you can take all the models from computer vision. Obviously, there is some tricks with resolution and if you take the sphere into account, yes or not. But in the end, it's a pixel, a segmentation task, and this is definitely not true for many CFD related tasks, because the task there is from a pure numerical perspective. You have a geometry which you can characterize with couple of parameters, probably less than 100 even, and then you get these full-fledged flow fields around and on the car, so that the actual input to output ratio is very different. And we don't have architectures, we don't have frameworks, we don't have an understanding of how to tackle that, but that makes it so exciting, I would say. And maybe thirdly, if you really look at these weather models and what they can do with hurricane predictions and so on, obviously there's always room for improvement, and obviously you can go further and further. But if you just look what happened in the last 2 years, and the resources on weather are, I would say, as tiny fractions to the resources in LLM and video generation, you see this tremendous progress in what hard problems and hard multi-scale problems we are already able to model, and which we can able better than numerics. So it's very clear that if done rightly and if the right incentives are there, this progress in this type of complexity we are able to do in CFD. Obviously, then we have to play the game numerics and ML together, which is then, I think, the hardest task to answer.
Yeah, that does seem, I guess, the joke that the Earth is always the Earth, and so the geometry is sort of, not so much the problem. And yeah, I guess it all depends on what is the data. You're right. In the CFD example, the geometries could be hugely varying, and that link between the geometry and the volume is it's the geometry and the boundary conditions is ultimately what affects the flow. So where have you seen? I guess a lot of people listening to this, and myself included, probably had their first introduction with what the DeepMind team did with mesh graph nets. There was obviously stuff before that, but that felt like the bit when everyone stood up and noticed. Why do you not feel that is the right approach?
It's always right or wrong. It's always hard to judge, but I think the mesh graph net and graph neural network simulators from the Peter Battaglia group were tremendously important milestone in this field, mostly because they were writing down this learning problem. And I myself went into this field of simulations because of these papers, trying to model particle systems. What we noticed back in the days, this is like 5-6 years ago, that it's tremendously hard to model all particle interaction as numerics is doing. So if you have this 10,000 system of particles and they interact, and you have something like a graph neural network, and you have to make all these interactions correctly, because otherwise the temporal integration will just go crazy. That's just a very hard learning problem. This is not what machine learning is really good at. Machine learning is good at to understand the global dynamics, to understand the behavior of the system, to understand where things are going on a global scale, but not on a particle scale. So I think from setting up this learning problem, this was a tremendously important step. Obviously, new ways of models are coming the way. For me personally, it was a big breakthrough that we started to see things as fields. So everything in my head is a field, and because a field is something which evolves over time. It can be an occupancy field, which tells you where is mass, where is no mass. It can be a signed distance field. It can be a velocity field. It can be a displacement field. Whatever field you want, but it's much easier for a model to tackle. Which is actually obviously the next step if you think of this whole scientific machine learning and neural operator and so on and so forth. And in the end, this is also how you model the weather. So I think conceptually for me, I don't know how it is for others, understanding that you can model large scale systems as a field was breaking a lot of boundaries in terms of scalability, because if you model a system of 10 million, 100 million particles as a field, it's computationally not a problem. It's from a learning perspective, it's not a problem, because you just don't need all these particles. You learn the dynamics with a very heavily subsampled representation, and obtaining the full field is also not a problem, because this exists. So I would say for me, understanding what machine learning is really good at and what numerics is really good at, and playing those two on those two fronts was making the difference. Yeah.
Well, one thing that I've maybe would appreciate you explaining to the audience, And maybe let's first introduce some of the work that you've done in this recent paper of yours. So you developed this transformer based approach, what do you call it? Anchor based universal physics. Well, maybe you explain what.
Yeah, we have
ABUPT.
Yeah, we have actually a couple of works. So one is which we call universal physics transformer. That's basically how we do latent space modeling of large scale system. Then we did something which is called neural DM, where we applied those to multi-flows and multi-particle systems. And then we recently applied this to large-scale CFD, similar framework, similar approach, which we call anchored branched, because these are the two ingredients which we need to do in order to get this to work on large systems. Exactly.
So in that context, what I'm hoping you could do is maybe explain a little bit, because there's a lot of people who listen to this podcast who are maybe not ML specialists, but are CFD primarily specialists who are now, more and more interested in ML and maybe actually developing it and are sort of progressing. And you mentioned a really interesting point to me, and I'm hoping you can explain this in a way that is understandable by others. Is that I guess some of this is a maths exercise, but and I've been guilty of this sometimes. There's this hierarchical thought process of being like, okay, you've got some sort of graph-based thing where it's more like point to point. Then you've got a neural operator where it's like more to solutions or fields. And then I initially thought of, okay, and then you have transformers. And yet you see some people who say, well, everything is a neural operator if you do the maths or design it. So can you explain and maybe dive a little bit deeper into that concept of solution mapping or field mapping, and then how it relates to transformers? Because I think it is a little bit confusing for people. So if we could maybe get into that would be in the context of, let's say, this drive ML or car, however you want to explain it.
Yeah, happily to do so. So for me, a neural operator, and this is also how it is introduced, is something which maps between function spaces, which is very which is not very informative if you because what does it mean you map between function spaces? But I always think of it as you have two functions, one input function, one output function, and no matter what you sample from the input function and what you predict on the output function, this has to be fulfilled. Meaning that if I sample 10 points from the input function, I should be able to predict as many points as I want from the output function, and those points I predict are actually on the output function. If I sample with the same network, with the same operator, 6 points from the input function, I should also get the same 10 points, and if I want more points, I get more points on the output function. Obviously, there is a limit. If I sample too little input points, then obviously the approximation network is not able to really get the information it needs. But if this sampling limit is reached, no matter how many points and where those points are spaced, it should always give you some sort of representation which allow you to construct the output function. So in the latent space, this mapping is then so to say resolution agnostic, and that with some small tricks you can do with convolutions, with Fourier neural operators, with transformers, and so on and so forth. And obviously transformers with their permutation.
If I just interrupt you just for 1 second, just to make it even more clearer. When you say sampling the input function and the output function, by input function, you're meaning like the geometry surface in this conceptual sense, and the output function being, let's say, the volume. Would that be one interpretation?
Yes. For example, you can think of it that the input is the geometry, and the output is either the field on the geometry or the field in the volume, or both, actually.
And the idea of this, so where, this sounds like a bit of a, I remember when this first came out, I think it was billed as a resolution independent. So which always to a CFD person feels like the no free lunch sort of theorem. Like, how can this possibly, how can that be true? You're basically saying, I don't need to map the entire geometry. I can just take a few and still get the same answer. So, where's the catch, I guess, on this?
Yeah, I mean, that's a very good point. And I think I can make my point very clear with really now going to CFD. And before that, I really have to say, if people think of resolution, we always think again of this segmentation as we do with weather, right? You have a certain number of longitude and latitude points, and if we double those points, do we get higher resolution, or do we just have an interpolation, and so on and so forth? So can we just run our whatever UNet and interpolate between this resolution, or is there a way to get this stuff resolved? So there's always this input-output mapping. And obviously, it will end up with interpolation effect. So either you interpolate somewhere in your network, or you interpolate on the output grid, because you, as you said, no free lunch. But if we go to CFD, things are a bit different, especially that the input-output resolution, as I said before, is very different, or input-output connection. And actually, we show in this recent paper that if you subsample a few of the points, so both on geometry and surface, and you do some training, there is a certain amount of points where the performance stagnates. So if it's for TribeML, this is roughly 128K, I think, or 256, I don't know by heart. And if you then add more points, the performance is not getting better, because all the information which the neural network needs is in those points. And if you sample it, let's say, cleverly, so that the distribution really covers the whole surface and the critical parts, and also points at the closer to the surface in the volume are represented correctly, all this type of stuff. But there is a certain amount of points where you really capture the whole phenomenon. And that's the resolution invariant, so to say. Obviously, if you go lower with the points you sample, you lose a bit of representation. So you don't resolve the full physics. So you're never able to really recover the whole physics. But there is a certain amount of points you need, and this is for each type of physics problem, that you have the full information in the network. And then obviously it depends how good your network is. And then obviously it makes much more sense to not have a network which again spits out these 128 points, but which conceptually is able to spit out as many points as you want. Because that's the neural operator, right? That you can really get every point on the output function if needed. And this is something which is very, very interesting in CFD.
Yeah, so I guess, again, correct me if I'm wrong, if I'm distilling this correctly, is you're saying if the surface in reality has 8 million points, or whatever the exact number is, you're saying that you should be able, by training and sampling progressively different points, you shouldn't need more than 256,000 to actually do as good job as 8 million. Whereas I guess with the analogy, I suppose what I'm trying to pick out is with mesh graph nets or with graph neural nets, people could in theory take 8 million, but they would normally like downsample. But they're downsampling, at least correct me if I'm wrong, you are then changing the problem statement in
yes.
It will give you a different answer.
Yes.
And that I know was certain experience that we had and others have had, where you go, well, how much do I downsample and where do I pick the point to downsample? And so a lot of people take an 8 million cell, can't fit it in a GPU memory and take 500,000, but they're worried when they do inference, they then would have to give the exact same mesh distribution, or if they give a different mesh distribution. Do you know what I'm getting at?
That's lovely. I mean, you said the most important point, which I forgot. Obviously, if you have to calculate something with drag or lift coefficient, for which you really need to get the correct value, you need the full simulation mesh, the full 8 or 9 million surface mesh. And obviously, the network has to give you this full mesh, because otherwise you're never able to calculate correct drag and lift coefficient. But the network is giving you this full network, this full drag and lift coefficient on the full surface mesh, no matter if you give it 64,000, 128,000, 256,000 input points. It's just at some number of input points, the output is stagnating, or the performance is stagnating, because you have reached the maximum performance. And the input, And obviously you can also give 8 million input points. The self-attention will be terribly slow, and I don't know what parallelization tricks you need to do. But nevertheless, it will give you the same answer in the output. So you can drastically reduce what you give as input, as long as the output still gives you the correct answer. And that's the magic we got from transformer, which we cannot do with other methods. So for other methods, we really had to make the problem much easier, which is obviously giving you the wrong physics.
Mm-hmm. So if we now move on to, and I guess this is the novelty that I saw in your approach, and I thought it was good to double click on a bit, is why the transformer? What specifically is that architecture giving you versus alternatives? Because, yeah, and how that relate. If you could maybe go into a little bit, because transformers, I think most people know conceptually, tokens, etc., LLMs, but maybe not in the context of CFD.
Yeah, so transformer are tremendously flexible, tremendously optimized, and tremendously well understood power horse in deep learning, right? They are the engine behind large language model, computer vision, and all these tricks are already done. And they have a few certain properties which are super nice. The first is the invariance with respect to sequence length. So no matter how long the sequence length is, which corresponds how many points you input to the network, it will do the same calculations, right? Which is very important for the scaling properties. Then they have this, how to say, so I call it discretization conversion. So if you sample more points in an area, it is basically, it will converge to some field. So the more points you sample, the better the resolution gets, which is obviously extremely valid, important property for this null operator paradigm. They are made, so the transformer paradigm is made and stress tested again and again and again for scaling, meaning that you can build larger models, that you can ingest larger data sets. Yeah, and all these things make them an ideal fit for us. I mean, I'm very happy that not everyone is using transformers. That gives us some edge. But yeah.
But specifically, so how do you tokenize the problem then? How could people conceptually understand, mesh graph nets conceptually was I have a node which corresponds to my mesh. I have some edges, and then I take that. Like, you're not taking a token per node, clearly, or that wouldn't scale, right? So how could people conceptually think of that sort of tokenizing the surface or the volume?
I think that the way you have to approach this is not from a physicist perspective, but from a computer vision perspective. So what do people do in computer vision? So I think when you do something like image generation, where you type in a prompt, I want a horse in the woods with whatever. So you have some text, and then you mix that with some image which is generated, right? So you have basically two streams. And the second important part is this concept of patching. So the transformer, for text, it's very clear. Each word gets a token. So each word in a sentence, or probably each sign or whatever, is tokenized. For images, small patches of the image will correspond to a token in a word. So everything is a token, which then can interact with each other. But in language, it's the tokens is words. In vision, the tokens is small patches of an image. So if we do the same thing in CFD, what we actually have, we have basically three types of information. We have the information of the geometry. So in general, what geometry we have. We have the information of the volume, and we have the information of basically the physics on the geometry. So it makes sense to treat this as either two or three modalities, as we call it, right? So as you have text and image, and then you can tokenize either small areas, which makes sense if you look try to encode the geometry. So small neighboring areas get pulled into one token so that you have this information which gets locally aggregated. Or you can, for actually doing physics, you just take samples of the mesh and see them as a token. And then you have the same setup. You have different tokens. They represent different physics objects or parts of the physics. And then similar to what people do in computer vision, you let those tokens speak to each other. You let, like this volume tokens between each other and the volume tokens to the surface and so on and so forth. So it's really borrowing a lot of concepts from computer vision because that's how it works. So
if I understand it correctly, essentially what you're doing is patching. So if you were to look at the surface mesh and if you have, visually, if you looked at it and you had a clump of 5 by 5, and you would have, 25 cells, and however many edges and nodes, you would say, okay, well, that can just become one token, and then you go into the next and next. So essentially you're able to go from 8 million points, and instead of taking 8 million tokens, you would have, 10,000 or whatever the number is. Is that, and the assumption is that the differences within that patch should be small enough to be not important. If you were to take too big a patch, I assume you would lose some accuracy because you're losing some local information. Would that be fair to say? There comes a cutoff point.
Yeah, so if you talk about representing the geometry, what you correctly said, you can do two things, right? You can treat each point of the geometry individually. It turns out this TribeML data set and so on and so forth, the information is so rich. So in order to really represent the geometry, you need roughly, 500,000 points. So it makes sense to pool them before, to aggregate them locally, and then to use those as tokens. That's just computationally much more efficient. To have some sort of pooling that the number of tokens is not exploding. You could also obviously use representatives of the geometry as your points, but it makes sense to pool them before.
And the same in the volume, right? You're essentially, instead of taking 130 million nodes, you're breaking them into patches, which themselves are taken to.
Yeah, the funny thing is, so there is this two. So we always have the number of points which it takes to represent physics correctly. This is two slightly different things. So for the geometry, we really need a lot of tokens in order to really capture the geometry, because the geometry is influencing the physics and so on and so forth. For the volume, we don't need so many points. So we only need roughly 128,000 or even less to really capture the physics. So we are totally fine to pick those points individually. And actually performance is not degrading much if we go to 32 or 64,000. That will get more interesting if we get even larger data sets. But then you can also use some tricks. So there it's obviously fully fine to use individual points.
So in that context, is it fair a mental model is that you're saying that the number of points that are needed for a numerical solver should not be a one-to-one mapping? That you shouldn't think just because I need 500 million points to solve my PDE that I should need 500 million points for my machine learning model to learn the behavior. That we need to break from this concept of almost one-to-one mapping. Is that part of your argument? Because that's not most people that I think assumed in the GNN that I need to have this sort of one-to-one mapping, that I'm sort of taking my nodes and I'm putting that into my ML, and that's the most logical way of learning the problem.
Yeah, so I really like those questions, I have to say. So my argument is, and I mean, you tell me, you're the CFD expert, but I would say what a model has to be able to do is it has to produce the simulation mesh. So it has to give you predictions on the simulation mesh, both on the surface and in the volume. And this is not only cars, it should hold for airplanes and so on and so forth. And if we think of meshes which approach 1 billion of mesh points, and where this is number one condition, we cannot use parallelization here, because then we end up using 1,000 GPUs, and this is not scaling very well. I'm looking at the actual information content. So it has to be, the model has to be able to produce this rich outputs in order to be a good tool to use. But on the other hand, you don't need this huge output for training. You can train on much smaller subsampled version of the same problem. However, you have to make sure with null operator learning, with function approximation, that those models you trained are then in inference or in test time able to give you the full answer on the full simulation mesh. I think this is the true CFD problem, or the true learning problem, similar to the error 5 setup in weather modeling, which we have to do in CFD.
So so this is an interesting point that it's good to maybe briefly discuss, which is at inference time. So we discussed about at training time, what do you take, how many of the points, how many do you agglomerate, et cetera, et cetera. But I guess what you're getting to now is the inference time, which is something that maybe is not so obvious to some people, but for me was always a bit of a conceptual challenge, which is, how do you generate the mesh to do the inference on? So normally, if you are running a normal CFD problem, or you're taking the driver ML dataset, you split it into a train and test. But both of them already have a mesh generated. We're giving it you. So you already have the mesh. But the real life engineering problem is, I want to predict a new geometry that I've never seen before. And the question is, do I have to mesh it like I would mesh a CFD problem? Or can I just take the CAD? Or can I just do some arbitrary case? Am I understanding it right that this is sort of your argument of the neural operator, or the field sort of based approach, that if I take a new geometry of a new car that I haven't done anything before on, and I mesh it 5 different ways, and then ask your model to give me a prediction, it should essentially give pretty much the same answer for those 5 different ways of meshing it?
Yes, I think this is the true power to
a point.
I mean, 2 things. One thing I haven't said. So I was talking about the difference in training and inference mesh. I also should say, for us, it's very important that the algorithm we are developing works for CAD geometry. So if you input in inference only the CAD geometry, you're able to obtain the full surface and full volume without giving any information of the surface and volume mesh in inference. The only thing the model gets is the CFD input. Obviously, the performance slightly degrades, but I'm amazed how well that works. And you can do that by using, obviously, in training the simulation mesh and using some tricks on the simulation mesh, because obviously you need this information in some way in training, but that you can tell your model how to work with basically structured points in the volume and certain points on the surface, such that in inference the model is able to deal without any of those meshings. And I think this is somehow the true power of these deep learning models, because they can not only scale, you can think of that the whole CFD simulation is suddenly compressed to neural network weights. You just have to ask the model at which region in the 3D you want to have the prediction, but you can also do that from pure CFD inputs. And so no storing, no whatever, right? And yeah, this is truly exciting, I would say.
Yeah, I think that's one of the bits that I think is the true test, because if you have to generate a mesh, the real-time element of the prediction starts to go, because for many people, generating the mesh, the volume and the surface is itself quite a challenge. And I think most people would prefer to go straight from a CAD geometry, or at least be less sensitive, to the mesh. The only conceptual challenge to this, and I don't know if we've even discussed this before, but I'll just throw it out there, which I think still is part of the challenge in people's heads, is if you do a CFD simulation, you would expect there to be a difference with the mesh. Like it should give a difference. If I run that driver ML with a grid that's half as coarse or twice as fine, I want it to give a difference, because by having a coarser mesh, I have higher numerical error, which should affect the flow field. And if I have a much finer mesh, I should see a difference because I'm reducing the numerical error. I think where it gets a little bit harder with the notion of sort of resolution independence is it sort of breaks from that mindset that I should be able to give you a mesh that's twice as fine or twice as coarse, and yet I get the same answer. It sort of messes with the CFD mind, because you think it should be different because I'm expecting in my normal PDE solver for it to be different, but it's not with ML.
Oh, I mean, actually, this was one of the reasons how we developed this anchor tokens. We call them anchor tokens approach, because this very much is, I think, the neural analogy of what you're saying. So what these anchor tokens are, and basically they are the reasons how we can scale. So we train on a selected set of tokens on the surface and on the volume. And those tokens, as we already said, they need to capture the physics. So it needs to be a certain amount, but they are sufficiently well to train with self-attention, everything on transformers. In inference, however, what we do, we pick these tokens. Those are representative points in the whole 3D volume, both on surface and in volume. And then basically those tokens span the weights of the keys and values. So in the transformer, you have 3 different blocks, and those span 2 blocks. So you do a first pass of the model with those tokens, and then this is fixed. So you basically have what you have built is you've built a model which is a representation of your full flow. And then you can ask for specific points in the volume or on the surface to get another value. And these points can be arbitrary points, any point. And this point will just run through the model with all these weights already fixed. So it only, like a small part of the model is adjusted, and it will give you an output. And obviously, the more anchor points you have, the finer this resolution gets, the better this prediction are, obviously until a certain threshold, right? So if you think of 16,000 points in the volume, you can still reconstruct the full flow field, but it's not the full accuracy. If you go to 32,000, 64,000, at some point, if the training allowed it, you will have the full field covered. And then with these points, you can get arbitrary fine resolution, and similar to in CFD, and you cover all the points in space. I think I see these anchor points really as some sort of these computation cells in CFD. Obviously, the discrepancy between number of mesh cells you need in CFD to get the simulation to converge towards anchor points you need in order to cover the full mesh is drastically different. But it's just because AI is drastically different than numeric simulation. But there is this analogy, and obviously if you don't use any of these points, it's very, very hard to construct these dynamics.
Yeah. I think conceptually some of the interesting challenge of that is, correct me if I'm wrong, but your ground truth is your train data. So you feel that if you match the train data, that's the best it can be, right? But the training data itself is dependent on the mesh. And so one of the, I guess, research topics that people have discussed is, well, how about multi-fidelity? So you have some high fidelity data, some low fidelity data. But how, I'm sort of going off on a tangent on this a little bit, but one of the things I always say to people is, if you have a concept of like a foundational model where you're saying, okay, I'm going to have a model that predicts cars, and unless my mind is just too static, it's a foundational model, but just for the mesh design that you've picked and the CFD method you picked. If I then go and change that CFD method and regenerate the driver ML with like a RAND data set, I'm going to get a different answer. So it's sort of hard to conceptually imagine the ML being like a foundational model, because the input data itself is so dependent on the settings you have of the CFD. So ideally, it should really be like experimental data. It should be the real ground truth. But it's sort of a little bit of a philosophical thing where, yeah, the ML model is only as good as the training data that it has. And so if now you've sort of solved the ML problem, well, I'm not saying you've solved it, it's almost the data is the most important bit now. You know,
I couldn't agree more. So I would say talking about foundation models for engineering is very, very dangerous, because you're kind of data agnostic in a way. In the end, what goes into these models is a huge amount of knowledge in this data generation. And as you said, data or numerics is not the ground truth. It's just one version of our reality, right? And machine learning is not replacing whatever this version of reality. It's giving a certain new access to this reality. So I think the power of machine learning comes when you really pick certain areas where it's tremendously important to have these surrogates and to have this fast iteration, and to have whatever, and then really think what it takes to build those surrogates. But I think from a modeling perspective, we are, especially in this static systems, we are pretty far that we can give them enough data and high fidelity data and so on and so forth. We can build these systems with reasonable errors compared to the data is trained on. The question is then always how to interact with numerics. So depends on what you want, but I think that the power and the true transformation comes when numerics and CFD really go, and deep networks really go hand in hand and not as two different parties. Maybe I should also say to that, we were doing this Drive ML data set now for, 10 months, like quite intensively trying different things. We've reformulated the learning problem ourselves a couple of times. So what we actually want to train, what we actually want to test, and so on and so forth, because it's really, really hard because it's just not a replacement of the CFD. Your model is just doing something different, and you have to frame that as a problem. And so that's why I think these two fields need to come closer together, that these questions are answered.
Yeah, no, I was just looking off to the side because I was just double checking if I was correct that the Era 5 dataset is a combination of actual satellite data, right? Observations with some sort of modeling. So it is quite different and I think that's kind of my point, that the weather stuff has literally got what the satellites is seeing. Therefore, you could argue is the real thing, because it is the Earth. They saw what the weather's doing on the Earth. Whereas in the CFD, it is just a numerical simulation. And so that's the bit that I still think is a bit of the limitation. But we are so sparse when it comes to data. This is a bit of a segment into a next question to you, which has long been the argument of the PINs people, which is, are we ever going to have a vast quantity of data to train sort of data-driven models? Is that a reasonable assumption, or is it better to say, well, actually, we have pretty well-defined equations and rules and models, and is it not just about using ML to solve them faster? Like, do we need, if we have such a sparsity of data, do we not need to include physics into the models? Where do you sort of lie on that conundrum of just generating more data and let the model do the data, or do we need to incorporate more physics into these models?
I'm very pragmatic in this. I mean, this was the same in weather modeling. Everyone was talking about physics informed, not physics informed, but people only talk for that amount of time until they realize how heavy the data loading is and how hard of a machine learning problem that is. Because you don't want to talk about a physics-informed neural network if you have to juggle between loading gigabytes of data for one data point on the GPU and what to do and in order to get this correct and in order to get a decent learning signal and so on and so forth. And I see it the same for these engineering simulations. We first have to be able to really run simulations at scale. And I'm not talking about 10,000 cells. I'm not talking about ShapeNet. I'm not talking about even DriverNet or DriveML. I'm talking about airplane simulation, and I'm talking about transient simulation, and we are still far away from doing that, both from how we generate, how we store, how we train data. And I think only if we are able to really have a workflow there and know what it takes and know where it breaks and where all these problems are, we can then start thinking about which type of physics to include and which not. Because we also showed that in our paper. It's very easy to build a divergence-free model for vorticity because you can bake in the divergence-free constraint per construction, a hard constraint. We tried a pin loss for the mass conservation, which is much harder, which just degrades performance. It in principle works, and you would need some tricks. And I would say getting this to work is not the amount of time which needs to do all the scaling. But I would say the problems we have to solve first are the really how we interact with numerics, how we scale to these problems, and how we actually get industry ready.
Well, you mentioned at the beginning the sort of T to T+1 analogy when it came to weather. And clearly the bit that we missed out maybe in our introduction is that for the engineering, we're not doing that, right? You're going from, straight to a time average or something.
At least in CFD, yeah.
In the sort of way that most of these data sets for cars and planes have been to date given. How would you change the learning problem or the ML architecture if now you had a full time history? And would that help, hindrance, not make a difference?
Same argument as we have in the spatial. If you look at the neural network, which has a few megabytes of weights, and which compresses, the gigabyte CFD simulation, or 10 or 20, or I don't know how many gigabyte actually, CFD simulation, you can also play the same game over time, right? So neural network is just a very, very good way of storing this information. And if you somehow manage to store the temporal part in some sort of modeling, which allows you to give you the temporal answer to a certain problem, this would be tremendously huge gain, because suddenly you can really simulate stuff in real time, but also have the ability to observe what's going on and to really understand the temporal dynamics. Whereas the training is just somehow pumping this simulation into the neural network weights, ideally without storing them, but that's very, very hard and probably the next step. But I think a first step is to get a decent neural network architectures for temporal modeling, which we are actually working on, to be honest.
Okay, and would you have the sense to be something similar where, you may want to have 1 million time steps, but that you'd expect that there would be some way of, I don't know, is there a sort of equivalency in terms of at inference? Ideally, you wouldn't need to go 1 million steps, right? Do you have a sense of how much? This is more a question for people who are generating data. Do I need to generate 1 million time steps of data so that you can learn the million? And do you expect that then you would be able to predict to the millionth, but skip out every 100 because you don't need to do that? Do you think you could learn the temporal problem without every single time step from the traditional PDE? Do you know, I'm trying to get a sense of how the temporal challenge would link to the spatial challenge?
I think it's very much relatable. So in space, we see this phenomenon that you don't need all the points to capture the physics. And then then you have a huge advantage in learning, because you can always subsample different sets of these points, which give you a huge data augmentation. And you have the same in the temporal domain. You don't need each time step in order to present the full physics to the neural network. But obviously, the fine grain, the more fine graining you have in your solution, the better you can do the data augmentation in the temporal dimension. But obviously, machine learning models can do much bigger time steps than numerical models. And yeah, this is something which is a true advantage. They just don't work the same, and they don't have stability issues, but also no stability guarantees.
Well, I was going to say, isn't that one of the problems, the rollout problem? That, I guess if you do inference, isn't these sort of instabilities going to build up, or how do you constrain it? Is this where some of the physics needs to be added, do you think, to sort of, if you need to do 100,000 iterations, how much are you going to guarantee that just a small difference in that first is not going to, bifurcate into different solutions?
Yeah, I mean, there is two answers to that. One is obviously luckily people do video generation nowadays, so we get a lot of tricks of video generation, which actually really start to make this thing stable. One of these definitely modeling paradigms is this generative model, that you model the distribution over time and that you kind of make sure the distribution always stays the same. And this boils down to a bit of physics understanding, right? If you make sure the distribution is the same, if you make sure that future and past are considered, that there is a tension across the right axis and so on and so forth, you get stability. It always depends on how you define physics. For me, it's the information the model needs and the way you interact with future and past and so on. I truly think that this generative modeling is the breakthrough in this rollout stabilities. I remember when I ran first into these rollout problems, it was, I think 4 years ago. And basically I did this paper together with Daniel Worrell, and I texted him and saying, hey, I don't know, we have to do something. Our rollouts are always exploding, and then I have no idea. And he said, well, yeah, there has to be some tricks in literature and something smart, and definitely people have thought about it. And I was like, yeah, I cannot find anything. There is why is nobody having this problem? And it's basically just a very different problem we have in this engineering task, that the input itself, each time step, is so huge from information content that every autoaggressive model, every autoaggressive trick you had before is just not working, because they work with much smaller input vectors. But now that computer vision is going to videos and that people are aware of this problem and that frequency spectra need to be conserved and so on and so forth, there's really a lot of progress. And I would say that having the frequency spectrum stable is what made many of these things stable.
So it sounds like, in a way, there is still a lot of potential to learn from the other advances in ML. The fact there's always an analogy problem, I guess, is what you're saying. There's stuff you can learn in terms of video generation, text generation, weather, climate. You can borrow ideas from other fields, but it suggests that you therefore need to have people with a broader ML background. If you just have a fluids background, you may struggle to solve this problem, because you need to know or you need to have an understanding and an interest in looking at what's video generation doing, or what's this doing. Would that be fair to say? This is why it's a multidisciplinary problem almost, or you need a team that is multidisciplinary?
I mean, that's happening in biotech and in other areas as well, right? We are just very agnostic to that in language and vision, because you don't need a linguist to build a LLM, and you don't need basically I don't know even what the computer vision what's the analogy there. But for all this AlphaFold and so on and so forth, they surely had domain experts on the team, and surely this is what's the exciting part about engineering. You have problems which are so hard to crack that you need top-notch machine learning people, the top-notch domain people, they need to speak the same language. And even if you can borrow a lot of concepts, they need to be heavily adjusted, because the problem with these large meshes, with what's the input, what's the output, there's this huge ratio difference and turbulence and whatnot. This is just a totally different beast to crack. So that's what's the exciting part here.
I wanted to maybe pivot it a little bit to the process you went in creating a startup. I think a lot of people would be interested to know, and I'm sure other people, are in a pub, or, alcohol doesn't need to be involved, of course, but, they're somewhere and they've got ideas, but not many people actually go out, secure funding and, create startups. So obviously not giving away any sensitive details, but what was that experience like for you? Like, how did it begin? How did you deal with venture capital companies? I'd be interested if you could share some of your experience in founding a startup, some of the lessons learned, maybe.
Yeah, so I was really lucky. So first of all, a lot of knowledge comes up from my university. I have to say that people like Benedikt Alkin and Tobias Kronlachner, who are really, really pushing the efforts, they have been with me from day one. Actually, also people like Steffen Birker here in Linz University is a well-known simulation expert who knows all these tricks. When I met him the first day, basically after returning to Austria, we were 5 minutes and we were both like super excited that we do things in this area. And yeah, there was a lot of momentum there. We were at a different company, NXCI, where at some point it was clear that the simulation team, which was really working well, should branch off. I was also lucky to have met people like Dennis Just and Mix Mikkelsen, who did this before, who created startups, very successful startups, and actually knew what to do. They were also the first who listened to me when I told them, hey, this engineering, like scaling these things up, what we do to this billion of mesh problems is actually what industry needs. But just give us some time, we will figure that out. And so I think this was all very natural. It was not planned, but it's obviously a huge excitement if you can do what you're really burning for in also in a commercial setup where you really can make an impact with what you're doing. So yeah, I would say in that sense I was very lucky, and I would also say that especially in this area we see a lot of momentum generated, and we are not the last startup, and there is hopefully coming more. There is a momentum, especially in Europe now in this area, and yeah, it's just very exciting. I would do it exactly the same way again.
And so how, do you think you could have done this any other way? Do you think you could have come up with what you're coming up at a company or at the university? Or is the startup really the only way of? I asked this question because I asked the same thing to Max Welling, and he was sort of saying, well, yeah, startups is the only place where this can happen. A university is either too small and doesn't have enough funding, or a company is too big and too slow, and the startup is this sort of, but it feels like in Europe we're often a bit risk averse, and we almost feel like startups is for somebody else. But I'd be interested to know your thoughts on that.
I'm not so sure if what we are pulling off, we just need the best people and some compute. One thing which is really, 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 really hard is the problems. So it's actually, we are choosing our customer mostly by the scale and size of the problems they have, because the really interesting problems come from industry, and the more challenging those problems are, the better they are for us and for developing us. So obviously we now have a customer which have huge temporal problems where we have different modalities interacting, and this can bootstrap our temporal modeling capabilities. And this is something which you wouldn't get at industry, at university. So I would say it's a mixture. I would say for me, it really helps to get hands-on to the real problems, and on the other side, it just helps me to get into touch what industry really needs, and not sit in my ivory tower. I wouldn't stand doing things where I know people wouldn't use them. So this is a good, good mix. But I also have to say there is luckily some people like Neil Ashton who generate publicly available data sets that people can really start looking at that. We just have to give the community the urgency that they really look at the hard data sets and not a shaped net car.
Yeah, it seems like there is definitely a movement in the industry towards this machine learning problems. You know, every time I go to a conference, there's more and more people doing it, but it still feels like we haven't reached that inflection point. It still feels like you're either a startup or you're, I don't know. It still feels like we're not fully at that, inflection point in terms of mass adoption of this. I feel like we're getting closer. I'm sure you feel the same. You know, lots of industries interested, but maybe it is the data that's the issue. Maybe it's the Era 5 was such a large open data set that data wasn't the issue, and therefore people just got into the modeling. Whereas I feel like now there's been quite a lot of advances in, let's say, road car external aerodynamics. But road car external aerodynamics, I don't know percentage-wise, but it's a small percentage of the entire CFD domain. And yeah, it feels like we still need to convince maybe the whole CFD community to do more, to really advance it and make this a more systematic. I guess, would that be true to say that you can only work on the problems that you have data for? I mean, it sounds like an obvious statement to make, but I assume if you had 10 times more data, you could potentially go and hire more people and work on more problems, but you're not going to go and hire more people and work on other problems if there isn't the data or the willingness to do it, right?
And most people also don't know what to optimize for, right? So I think the industry or the real problems need to set the stage. They need to set the machine learning problem. Then we can start to think of how to solve it. But there is a momentum. People are still reluctant because getting a neuroscience paper is easier on a smaller data set than on a larger data set. But I think there is quite some movement and things are really changing. And also for me, it's kind of our philosophy that to be a bit open source, to show our models, to show what we're doing, to publish, because I think this is the way to go forward. Closed doors policy is not what gets progress. I mean, we see that the whole progress in LLM due to open source and so on and so forth. And I think this is also what will, not what should, but what will happen in this space.
Yeah, I must say that I do commend that you're releasing the data and the models open source is a novelty. And I think, it's good to see, because I like particularly your paper now. I mean, I think that has hurt a little bit of trust in the CFD world so far. Is that, as you know, the tradition, and I'm not sure where the tradition came from. If you develop a turbulence model or you develop a numerical method, whatever it is, it's almost always published. It's very rare, actually, for a model to make itself into a large commercial, even, ISV CFD code, and not to have a corresponding publication. It's sort of seen as like a thing that you don't make money on the method, you make money on the code. That's sort of been the thing, like OpenFOAM or StarCCM or ANSYS Fluid to others. Typically, the models themselves, you sort of know. It's more the little tricks that you might do, but then more the support and the code and all that. Whereas it felt like so far in the ML for CAE world, with the exception of a couple of individuals or companies, most of the startups have not published or made a thing of saying, here's our exact method, but we've implemented it in such a way that, do you know what I mean? And I feel like that's hurt a little bit of trust, because it's hard for someone to believe results if they don't see a publication about it. So yeah, I don't know if I'm alone on this, but I think your strategy of publishing more, I think actually helps at least CFD people to feel a little bit more like comfortable with it.
I think it's the only way around. And if I make a bold statement, if in the machine learning world where things are moving so fast, you're afraid that others are copying your stuff and overtaking you, you should probably reconsider your capabilities as a company.
Yeah, and the only thing I would say though, which is why I've asked you sometimes to up-level the explanations, is I feel maybe even the biggest barrier is just an understanding barrier.
Yeah.
That, you know, if you're a CFD person, you're probably going to read an ML paper and be like, I don't really understand this. That's almost the challenge, you know. It's like an education thing, is that the people making decisions or higher up may not even understand because it's such a different field, that is the challenge. So anything that you can do to make like, simpler versions of papers or like summaries of papers or education, which I guess comes back to why having a dual affiliation between a university and a startup is probably a good thing, because I feel that you need to be teaching and producing like open source teaching material to educate people as much as also producing commercial solutions. I don't know if you've noticed that when you speak to customers, that sometimes their just knowledge of ML is part of the blocker.
Yeah, but it's also the other way around, right? There's hardly any people who have a knowledge of the real domain expertise and knowledge of ML. Because only if you have a knowledge of domain expertise and you know what ML can do, you really find the problems where ML can really have an impact, right? And this goes in both ways. So education both ways is super important, and it's very, very hard. I mean, I see that myself all the time, that I get lost in details and think things are obvious. And on the other hand, when I talk to real domain experts, I get really lost and have to ask questions. And
Yeah. Well, maybe this is why it will take a few years to reach a greater maturity, because both sides need to upskill themselves and sort of learn. So great. Well, really appreciate you chatting. I mean, what I'm going to do is put some links in, at least on the YouTube, to a couple of the papers and the models that we've referred to, because I think people should really spend a bit of time looking at the papers. I have a feeling that, you know, we might need to chat again. I think this field is moving so quickly that everything that it'll be interesting to see if we listen to this conversation in a year's time, are we going to be completely wrong or in 2 years' time?
I very much hope so. But where we won't be wrong is that some things are moving fast, and that we will have fast progress in 2 years. So we will be, we didn't expect that to happen. So
yeah,
that's going to happen.
That's a good thing though. Maybe that's okay. But yeah, for now then, until we speak again, thank you very much. And hope people enjoy looking at your paper and your work.
Thank you very much, Neil, for having me.